There's something about airplanes that creates an immense human connection. You walk up to an airplane, a feeling comes over you. This is something that shouldn't work. Humanity came up with a way to do something that humans were not intended to do. It's an immensely powerful thing. These are pieces of technology that are like expanding the bounds of the human experience. At Hermeus, we're pushing the bounds of what's ever been done before with airplanes. We're building airplanes that will go faster and higher than any aircraft ever before.
High-speed flight has always interested humanity. Got to go fast. It's like it alludes to Ricky Bobby a little bit, but it's like that's the kind of like exciting part of what we're doing.
A question that we get often is why Mach 5? Why did we settle on that speed versus, hey, like what are speeds that fighter jets are hitting today? Why have we not hit it before, and why does Hermeus think we can do it now?
The pace of innovation has basically declined to near zero within aviation. And the ability to rapidly iterate to design requirements that are bespoke is something that doesn't really exist anywhere. It can happen in small pockets, but like we are turning cycles that people haven't turned in decades.
When we think about conventional turbojet engines, you know, what might be in like your F-15s, your F-16s, really what is inside of that is a conventional turbojet, which we're going to walk past here. You know, you have your compressor stage, you're taking in air from the atmosphere, you're injecting fuel, igniting that fuel, generating thrust, and spitting that out the nozzle. What we're able to do with these types of turbojets is we're able to create thrust at ambient conditions. Once you actually start flying fast enough, instead of having to compress that air to create pressure, what you can actually do is use how fast you're going and use the speed to compress that air before you actually inject your fuel and ignite it. So that's that ramjet section there. Any experimental ramjet that's historically existed had to be dropped by something going faster to get it up to those speeds. So what's different about what Hermeus is doing is bridging turbojet technology with ramjet technology, and that's where our turbine-based combined cycle kind of secret sauce comes into play. That turbojet section will get us to, you know, around like the low Mach 2 range, and then when we're igniting our ramjet in the high Mach 2 to Mach 3 range, we need something to help bridge that gap. And that's really the secret sauce of why is Hermeus saying that we can do something that's never existed before.
Welcome to Hermeus. This is our headquarters facility in Atlanta, Georgia. This is where we do the vast majority of our engineering, builds, integration, and tests for both our airplanes and our engines. Pretty much everything that you see is something that like a person from Hermeus built and put together here. It turns out it's quite a bit of effort to build an airplane factory. I'd like to start the tour here with an understanding of our beginnings. A gas turbine engine that operates at low speeds up to about Mach 3, and a ramjet that operates at high speeds up to about Mach 5. Something that hasn't really been done before, but our thesis was like, there is really no science around this that has to happen. It's all engineering. With a couple $1 million and about 8 people, built everything that you see here. It's normally designed to operate up to about Mach, 0.6 or so, about 20,000 feet. In a wind tunnel, we pushed it up to about Mach 3.3, so SR-71 speeds, all without really breaking a sweat.
So the first 6 months was really kind of proving to ourselves that there was a there, that there was something actually useful. We understood that hypersonics were increasingly important over the coming years and decades. But it was really like, okay, how do we actually build a business case that matches the technology? And so that's what we really spent the first 6 months proving out to ourselves, is like, we have to marry the finances with the technical progress. And that's where I think some of the biggest challenges in aviation and aerospace, or a complex system space, really is. And then, you know, starting to build the culture, building like how we tell people the story. That was a lot of what we were practicing as well. It's like not this like long-term vision stuff, but just like, how do we give a presentation to someone who doesn't have a technical background? We spent a lot of time talking about that and getting feedback and working on that. So a lot of it was very, very storytelling and you know, our own ability to communicate around this, you know, topic that's very niche.
One of the like core tenets here at Hermeus is really vertical integration. So when something exists off the shelf, is designed to work in the environments that we need to work in, then just use it, bring it in. So like the gas turbine engines that we just talked about, we're not going to reinvent those. Very expensive, very difficult. But a lot of things have to either be modified or designed from scratch. And those are the places that we really want to be able to do in-house. So part of what we've got here is our fluids capabilities. So these are like valves, actuators, things that are very bespoke to the vehicle or the engine that they're being used for. We want to be able to design, develop, test, qualify, and eventually produce all those components here in-house and save ourselves a massive amount of headache from bringing that out of house. We've invested heavily in metal additive manufacturing, so we can do both titanium, primarily for aircraft structures and components, and then Inconel for engine components. That allows us to have a really, really fast pace of iteration. So we're on the test stand with an engine, we break apart because we didn't know the environments well enough. We now learn something that we can redesign the part, build it, have it back on the test stand within maybe a day or so. Versus maybe weeks or months in a traditional way. So having a full, manufacturing capability of traditional manufacturing is also important as well to keep a very tight coupling between engineering, manufacturing, and integration. As you start separating those things, it becomes very, very difficult to actually engineer a very complex system very quickly. We set the goal of 1 airplane per year. That kind of sets a set of requirements for like how you build and run a business to do that. As we walk up here, you'll get a feel for the scale of engine that we're working on right now, which is the J85. So that's the engine that powers the F5 ENF. So if you've seen the original Top Gun movie, the black planes that fly against Tom Cruise, this is the engine that was in those. So that's this little guy right over here. Puts out about 5,000 pounds of thrust in afterburner. This is what we've built the first Chimera engine around. The next engine that we're going to is the F100. So that's what this big guy is right here. So significantly larger. This is the engine that powers the F15 and F16. Puts out around 30,000 pounds of thrust in afterburner. So significantly larger than what the J85 can do. And we're very excited to start our work on this engine and pushing it up faster. So this is the first fully integrated iteration of Chimera that we've tested and demonstrated in a wind tunnel on the ground. It's a really, really elegant dance that took us a while to figure out and sort out. But we've got that done. We can do it very confidently over and over again in about 5 seconds, which is super, super fast.
When I think about some of the technical changes and really the story of where we were when I joined the company to where we are now, it was constantly thinking about how do we actually think about what technical problems matter in the first place. I think a lot of times engineers love a science fair project and we can just dive right in. But I think really making sure that from a company perspective, we've outlined what are the right problems that we want to be chasing in the first place, and then distilling that down, breaking that down into, okay, now we have these specific engineering problems we have to solve.
Yeah, let's hit the airplanes. No airplane factory tour is complete without seeing some airplanes. One of the other kind of core tenets at the business is iteration, but at the system level. So we've built a company that can build an airplane in a year. That's kind of unheard of. The normal pace for that is probably 4 to 5 years.
Traditional aerospace programs are typically, roughly a 5-year program where you take off all the scope of an enormous amount of complexity, and then you have to incrementally walk your way through, and everything gets fleshed out over time. Costs and schedules start to run away because when everything is very serial like that, an issue here propagates all the way down, and the more complexity that you have, the more likelihood things propagate, and then, things are kind of exponentially running away. Limiting the scope and focusing everything in an iterative way allows us to constrain that, and then we're cycling at 1-year timelines to be able to deliver narrower scope than people might think, but ultimately you're saving those exponential runaways. Each iteration then only has the ability to run away a little bit, maybe 10, 20%, instead of this exponential 3, 4, 5x.
We've really kind of set the requirements to really fully rethink how we do aircraft development. That gives us a chance to really focus on one set of requirements and one set of risks per airplane, really get that right, and then move on to the next one.
So this is our Mark 1. So this is our first flight aircraft, the first instance of us becoming an airplane company. So something I tell the team all the time is you're not an airplane company until you have an airplane in the air. So this is our first at-bat with that. So it's a remotely piloted vehicle, so no people on board. Actually, the flight deck that'll be controlling this is behind you.
So we've got a number of really, really good flight test pilots on staff who have flown just about any aircraft you can imagine. And having them integrated with our engineering team is also awesome. We're in the early conceptual design phases of a vehicle, and the pilots are sitting there with the engineers. So when we go fly Quarter Horse Mark 1 this summer, this is where it'll be flown from.
So Dark Horse is the exquisite system that we're iterating towards, and all of the incremental versions of Quarter Horse, the marks that we're building, get us there. And at each point, we can fork off a product. Everyone, to be honest, I think hates flying on an airplane. It's funny to start an airplane company when I really, really hate flying on an airplane. Everyone would say yes to being able to fly fast, assuming you can make the price point make sense. We've seen it in aerospace. The new space approach is able to kind of disrupt price points. As we start looking into the aviation side, the airplane side, we really haven't seen that sort of price point disruption. I think for the long term, we've done some studies, and obviously there's a lot to learn, but there's definitely a world where we're able to be in the neighborhood of business class prices for extremely high-speed vehicles, assuming that you can bring the development cost down to where when you amortize that across the full life of a system in operations, you're able to keep the price point for the customer within, business class prices. However, for the next decade-ish, we're going to be really working on defense because that's where the near-term needs, the near-term problems need to be solved and where we can deliver a lot of value. That's also allows us to take a more incremental approach as well, which is like for a commercial passenger aircraft, the level of reliability has to be pretty extreme. The ability to understand maintenance, repair, and overhaul has to be very well understood. That sort of thing can't happen until we start getting reps at flight. And by building low-cost, high-performance, rapid vehicles, we're able to really start to understand those things. Additionally, it's like we're building entire life cycles with the team. By the time we are attempting to break the airspeed record, that's the fourth full system that the team will have built. It's not just the designers, it's also the test team, it's also the manufacturing team, it's also the entire business understands how to do the logistics of getting out to a deployed test operation, all of that.
So we designed, built, and integrated this aircraft in 204 days. So we missed Kelly Johnson's record of, I think, 143 days for the P-80 by a little bit, but I don't mind being second to the greatest of all time. So this aircraft, its purpose is really all about subsonic flight testing, takeoff and landing of a high-speed airplane. Make sure that we're very good at dealing with an aircraft like near the ground where you've made all these design compromises for high-speed flight.
Being able to actually take off from a conventional runway, being able to accelerate up to the speeds that we can turn on our pre-cooler, which allows us to bridge that gap to where we have our ramjet and we can ignite our ramjet, and then now we can start operating in a ramjet phase. That's really us completing a full regime of speeds, which is pretty different than what's conventionally existing out there.
You kind of have to build like a crappy subsonic airplane, a like kind of good high-speed airplane, and a very good transonic airplane that manifests itself in like really high takeoff speeds, high wing loading, and things that are like generally very difficult for airplanes to do. Being able to like reliably take off and land with remote pilot and everything integrated working together is really the purpose of this first vehicle. So this is the one that we built last year that we're flying this year. This year, we'll be building our first supersonic aircraft. So that one will do probably about Mach 2.5 plus. It'll exceed the speed of the fastest operational airplane today, which is the F-15. So that bar is at 2.5. And that record has been held by the F-15 since the SR-71 retired. Quite a bit of history that we have to go make going forward, but that's always fun. Keeps us motivated.